Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we are going to look at integrals and particle motion. So just like this was a big topic with derivatives, position, velocity, acceleration, distance, displacement, all that good stuff, it's going to be a big topic with integrals as well. But you're going to notice a lot of the connections are the same as when we used particle motion with derivatives. So let's just jump right in. We are going to cover a lot today. This video may be a bit longer than normal, but that's just because it's a big topic and you will see this probably all over your AP exam. At least that's the way it's been in the past. So let's just do a quick review. If I'm given a position function like this, p of t, how do I find the velocity function? Go ahead, find it. Then how do I find the acceleration? Same thing. Go ahead, find it. Okay, so to find velocity, v of t is going to be equal to the derivative of my position function, which in this case is 9t squared minus 2. Acceleration function, well, that is just the derivative of the velocity function, which is equal to the second derivative of the position function, which is in this case is 18t. So again, just reviewing those relationships between position, velocity, and acceleration when we're talking about derivatives. Now, we're going to be working the other way. So I'm going to be giving you a velocity function, and can you think about how to find the position function? Well, go ahead. If you can find it, and if you see something wrong or if you have any comments, think about those before you continue with the video. Okay, so if velocity is the derivative of the position function, well, if I work backwards one, right, if I take the antiderivative of the velocity function, that should leave me with the position function. And again, our notation for antiderivatives is just the integral sign. So the integral of v of t, I'm taking the antiderivative with respect to t, so dt, that will be equal to p of t. So let's go ahead and do that. I'm taking the integral of 5t minus 1, use brackets, and that is equal to 5/2 t squared minus t. Because this is an indefinite integral and not a definite integral, I need to keep my constant of integration, the c. But that would be my position function. And of course, that position function could be different depending on what my constant of integration is, what my c value is. So let's move on to the next page. We just came up with this. Let me see, we're not going to do number 4, so this will be good enough. So I know my position function is 5/2 t squared plus t, or sorry, I think it was minus t plus c. So that c is our constant of integration. And again, that could be a number of different values. That's going to depend on where the particle started. So when the velocity is 0, well, that would be what our c value is. The position of the particle when the velocity is 0, that would be our c value here. So let's think about that. Down below it says if p of 0 is equal to 6, then what would the constant of integration be? What if p of 0 was equal to -4? And let's show the work for both scenarios. So if p of 0 is equal to 6, well, if I have my position function, my general position function, and I have that initial value, right, p of 0 being equal to 6, well, then I can just substitute in, right? So p of 0 is equal to 5/2. I know this is going to seem rather trivial, but I am just writing out the work so we understand what's going on. Just substituting in 0 for t. And I was told that p of 0 is equal to 6, right? So I can set it equal to 6, and I get 6 is equal to c. So in this case, my position function would be p of t is equal to 5/2 t squared minus t plus 6. So if they gave us that initial condition, we could figure out the specific position function. All right, and sometimes they'll change it. So they said that the position when t was equal to 0 was equal to -4. So all that means is that I set the position function equal to -4 when t is equal to 0. So in this case, c is equal to -4, which means my position function, p of t, is equal to 5/2 t squared minus t minus 4. So again, the idea here is that if they give you a velocity function, you can find the general position function. The only way you can find the specific position function is if they give you a value or if they give you an initial condition for the position function. And they actually don't have to give you the initial value here or the initial position. They could just give you any point on the position function, and if they did that, you could end up solving for c. They just tend to give you the initial position most of the time. Okay, I guess our second main concept from today. The first one was that the antiderivative of velocity would be position. This concept being, how do we find the specific position function? We're going to skip number 4. We're actually going to do everything on this page. So another application of integration is finding the total distance that an object has traveled over a given interval. We looked at this topic back with derivatives. We talked a little bit about, total distance versus net distance versus displacement, and we're now going to revisit those three concepts. First, take a look at this graph and think about what this graph represents. Does it represent the position function, the velocity, and the acceleration? And it doesn't tell you directly, but it does tell you indirectly through the units that are given on both axes. Okay, so based on our units, our x is time, our y is miles per hour. So this is going to be a velocity graph. Because the y units are miles per hour. If they were just miles, then it would be a position function. If they were miles per hour squared, then it would be an acceleration function. Just miles per hour, that is how fast you are traveling, so that is going to be a velocity function. Next question is, could we use this graph to find the total distance traveled by the object over the interval 0 to 2? And if we could you write an expression for it? So the answer is yes, we can. So I want you to think about what expression could we write to figure out the total distance traveled over the interval 0 to 2. And think about using an integral. So we know that the area under the curve of a velocity function, in this case we're going from 0 to 2. So it's just this entire area here. We know that represents the total distance as long as it's completely above the x-axis. So in this case it is, so we can just look at the area underneath the curve. So if we were to write an integral expression for this, we would have the integral from 0 to 2 of f of x dx And again, we know that f of x represents the velocity here. Let's keep going. We already did number 7. That was just writing that integral expression. But let's look at 8. It says without using a definite integral, how would you find the total distance the object traveled for this graph? Again, this is a velocity graph. Could we use the same method for number 6 up above? Why or why not? So could we just write an integral here for the total distance? Think about why or why not. Well, the answer is we can, but it may not be the integral you're thinking of because it's one we haven't talked about yet. Remember, total distance is different than net distance or displacement. So if I just wrote, and let's quickly, let's see how far this goes. So we're at 5, 10, 15, 20 here. So if I wanted to find the total distance traveled from 0 to 20, right, you may think, okay, let's set up an integral 0 to 20 of g of x d of x, or dx rather. Well, the problem is this is going to skew the total distance, right? Because you have some areas that are below, you have some areas that are above. So you'd be adding some negative areas to positive areas, etc. And this would give you the displacement of the object. So this would tell you how far away the object was from its initial position, and it would tell you the direction, right? If this was positive, then it would mean the object ends up to the right of the initial position. If this answer was negative, right, it would just mean that the object ended up to the left of its initial position. And then whatever the number is, that would give you the distance, right? The positive versus negative sign gives you the direction. The number would give you the distance. So this right here, this would be the displacement of the object. Now, before we get to total distance, let's think about what our net distance would be, because net distance is very closely related to displacement, right? Net distance and displacement are the same, except that net distance always has to be positive. So if we took the absolute value of this answer, that would give us net distance. So let's say our displacement, because it does look like the area below the x-axis is more than the area above. So it looks like our displacement's negative. So if our displacement was like negative 12, our net distance would just be positive 12, right? Just the absolute value. Total distance is where it gets a little bit more tricky, right? Because total distance, you have to actually find all of the individual areas. So let me just make this a different color for us. You'd have to find the area of the pink, the blue, and the green, make them all positive, and add them together for the total distance. Because again, total distance, when you change direction, if you don't factor that in, that's going to throw off the total distance. So you would need to break your integral up over these three intervals. And then again, you have to find the positive areas of all of those and add those together. There's a couple different ways to do this. One is on your calculator. One is by hand. Calculator, it's quite easy. All you do on your calculator is, let's do this in brown. So on your calculator, you're still going from 0 to 20. All you have to do is put absolute value signs around your function. Okay, and if you think about visually what that is going to do, let me make sure we know this is equal to total distance. So what that will do is the calculator will then read this function as this. Right? Instead of Because if it's the absolute value, all of those y values will be positive. So your new function will be completely above the x-axis. And then it would make sense to just take the entire integral, right? Because everything is completely above the x-axis. So you don't have to break the integral up at all. So again, very easy to do on a calculator. When you're using your calculator to evaluate the definite integral, just put the absolute value signs outside of your function. The tricky part comes when you have to do this by hand, because then you actually have to figure out where the function crosses the x-axis and do multiple integrals, etc. We're going to do one of those examples together. Let me just talk about one more thing related to the calculator. So I know we've talked about, let me just erase all of this for now. If you were trying to find total distance, right, you would go, using a calculator, you would go to Math, and then you would go to option 9. This is if you're using a TI-84. What that's going to bring up, right, it's going to bring up something that looks like this. And then you would enter in the different pieces. So what you would do when you're trying to enter in absolute value, your limits of integration, those are obviously quite easy. So when you get here, before you enter your function, you would go to Math again. Then you got to go over to the Number tab. This is a tab at the top. And then you've got to go to option 1. If you click that, inside of here, you will get some absolute value signs. Then you can enter your function, whether you just enter y1 because you've stored the function there, or whether you enter, the actual function like 2x squared minus 5x plus 3. But again, you're going to put those absolute value signs in there first and then enter your entire function in between. Okay, let's do an example where we have to work this out by hand. And actually, I just talked about what was on this page up above. I just used example 8 for that. Here, again, we're just talking about the differences between total distance, net distance, and displacement. So you can think about number 13. What does this integral represent? Does it represent total distance, displacement, or net distance? Why are you choosing one over the other? And then we actually, let's just go through this. It'll only take a minute or two. But hopefully it'll solidify some of these concepts. So we'll put off doing an example by hand for now. We'll just finish this page. So like I said, pause the video. Does that integral represent displacement, net distance, or total distance? Well, this would represent displacement. And if the answer was positive, it would also represent net distance, depending on, if it was negative 12, it would only represent the displacement. If it was like positive 15, it would represent both displacement and the net distance. And this is because part of our graph is below the x-axis, right? This part of the graph right here is below. So that area is going to be counted as negative, whereas for total distance, we would need that to also count as positive. So if I just did this simple integral right here, this would represent displacement and maybe net distance. We just would have to look at the sign of the answer. So if you're trying to find total distance, right, you're going to have to take the absolute value of the velocity function and I kind of gave you a visual down here, right? And this is what I did with number 8. If you take the absolute value of the velocity function, all of your y values just jump to above the x-axis. So, right, instead of the velocity function traveling down here like it did up above, when you make it the absolute value, those y values jump up to those pink values. Then you could just take the integral from 0 to c of the absolute value of the velocity function. In this case, our variable is t, so we'll have a dt rather than a dx. So again, calculator, very straightforward. By hand, a bit more complicated. And finally, we are ready for that. We're going to do number 15. So this would be a non-calculator question. So just keep that in mind. We should be able to do the whole thing, no calculator. We are given the velocity function, 2t minus 6. First thing we want to do is find the displacement of the particle over the interval 0 to 10. Then we want to find the total distance traveled by the particle over the interval 0 to 10. Pause the video, see if you can figure out either A or B, maybe both, and then come back and join us for a discussion. Okay, so displacement's the easy one. Displacement, we can just do or evaluate the entire interval at once. So the integral from 0 to 10 of 2t minus 6 dt. That will give us displacement. Because I'm doing this by hand, I have to take the antiderivative by hand. And once I do that, I will be left with evaluating it from 0 to 10. Antiderivative of 2t is t squared. Antiderivative of negative 6 is negative 6t. Again, now I've dropped the dt because I've already taken the antiderivative. Now I just have to evaluate. So this is going to be equal to 10 squared minus 6 times 10 minus 0 squared minus 6 times 0. This will give me 100 minus 60 minus 0, which gives me 40. No units, so we can just leave it as 40. Now, because this is positive, this also represents something else. This also represents net distance. If it was negative 40, it would not represent net distance because, again, distance has to be positive. But when displacement's positive, that's also net distance. Now comes the tough part. We've got to try to figure out the total distance by hand from 0 to 10. So remember, we need to try to break the velocity function up by when it's above the x-axis and when it's below. So if I'm looking at a velocity function, and this one's actually pretty straightforward because it's a linear function. Our y-intercept is negative 6, and there's a slope of 2. So our velocity function looks something like that. So what we need to do, and if we're going from 0 to 10, maybe this is 10. And again, not drawn to scale or anything. But we need to break this up by 0 to c, and then c to 10. Right? So I have to find that point where the velocity changes signs, where it goes from negative to positive. And that's the point where I'm going to break up my integral. And I'm going to have to write, in this case, well, maybe there's going to be 2 integrals. If there were 2 c values, there would have to be 3 integrals, etc. In this case, there's only going to be 2 integrals because it's only going to cross once because it's a linear function. But there could be multiple places where the velocity changes signs. So let's try to find that c value, right? Let's try to find where the velocity is equal to 0, because that will, in this case, be where it changes signs. Let me set, you know what, let me get rid of all of this so I have more space. So we're going to set v of t equal to 0. So 2t minus 6 equals 0. I get 2t is equal to 6. I get t is equal to 3. Now again, I kind of showed you that the velocity was going to change signs at t equals 3. You could check just to make sure. We know we're going from 0 to 10. So if this is v of t, you could just check 2 spots on either side of 3. So you could do v of 2, it's equal to negative 2. V of 4, that's equal to positive 2. So we see that it does change signs. And again, this is to help you out, right? If the velocity didn't change signs, but it stayed negative or it stayed positive, then you wouldn't have to break your integral up, right? That c value wouldn't be important. It's only if the velocity changes signs at that c value do you need to break your integral up. So here's what our new integral is going to look like. Total distance. That's going to be equal to the integral from 0 to 3 of v of t dt plus the integral 3 to 10 of v of t dt. Now there's one more thing I have to add in here before this is completely correct. And that's some absolute value signs, right? Because when I looked at this function originally, so let me sketch that out again. It looked something like this. So one of our areas is going to come out to be negative if we do that integral. One of those is going to come out to be positive. But for total distance, I don't want to count those areas as negative, right? Because distance is always going to be positive. So what you can do is you just put absolute value signs around these entire quantities. So whatever number you get here, you need to make sure it's positive. If it's negative, you just change the sign. If it's already positive, you can leave it. And you need to make sure that answer is positive before you add them together. Notice that total distance ends up just being a sum of the net distances, right? This is a net distance because it's the absolute value of displacement. This is also a net distance as it is the absolute value of displacement. So if you find the net distances over intervals where the velocity does not change signs, the sum of those net distances will be your total distance. So now we just have to do these integrals by hand. Let me erase this to give us some more space. And you know what? I'm actually going to erase everything. You guys obviously don't have to because you have more space in your paper, but I just want to be real clear with what I'm doing. I don't want to try to squeeze it in somewhere. So our total distance is equal to the absolute value of the integral 0 to 3 of v of t dt plus the absolute value of the integral 3 to 10 of v of t dt. And yes, you may have realized from the graph, well, I know that this is going to be positive, so why do I need the absolute value signs there? Well, you don't if you know that that integral is going to give you a positive area. But there are some graphs where you may not know what they look like. So just to be safe, you just put the absolute value signs there for all of them, and then it's not going to matter, right? Whether you know what the graph looks like or not. So let's go ahead and start to evaluate these. I already know what my anti-derivatives are. Just put my absolute value signs here first. So I'm going to be evaluating this antiderivative, t squared minus 6t, evaluating it from 0 to 3, and then the same antiderivative from 3 to 10. Okay, now for the one on the left, I'll do that one in pink. So I get 3 squared minus 6 times 3 minus 0 squared minus 6 times 0 plus, I'll do this next one in blue, 10 squared minus 6 times 10 minus 3 squared minus 6 times 3. If I start simplifying, this gives me 9 minus 18 minus 0 plus 100 minus 60 minus 9 minus 18. Let's pop up here. It's a good thing I erased because I would not have had enough space. This gives me negative 9. You know what? Make sure I keep my absolute value signs. So the absolute value of negative 9 minus 0, absolute value, plus 40 minus negative 9. That gives me the absolute value of negative 9 plus the absolute value of 49. Have equal signs here as well. That gives me 9 plus 49. And that gives me a total distance of 58. So again, quite a bit of work when you're finding total distance. You got to figure out where the velocity function changes signs, and then you got to break up your integrals based on those c values. In this case, fortunately, there was only one. You could see if there were multiple c values, we'd have even more integrals to evaluate. I think that is going to do it for this video. A bunch of more problems to practice. We'll have some time in class to work on those. If you want to get a head start, you can. But I think we've covered all the big concepts related to integration when it comes to particle motion. So let's pause it here. As always, enjoy the rest of your day, and we will see you back for our next lesson.